Let me introduce about the next presentation. So next presentation will be about towards efficient neural rendering. So let me introduce Professor Sungjoo Yoo. So he received PhD from Seoul National University, and he went through all the famous affiliations such as tinyML Laboratory, Samsung Electronics, Postech, Facebook, and he is now director of Neural Processing Research Center, which is Samsung and Seoul National University Joint Research Center. His current research interests includes algorithm and hardware co-design of neural graphics and large language models. So, yeah. Let's welcome Professor Sungjoo Yoo.
Yeah. Thank you for the introduction. So the title is Towards Efficient Neural Rendering. This is a tutorial presentation on recent papers. So in the beginning, I will introduce neural rendering, and then I will present a performance problem, and then recent improvements of computational efficiency, focusing on two technologies, Voxel grid and mesh. And then I will summarize my talk with some prospect on future work. So on this kind of mobile devices, we expect a photorealistic experience for entertainment and productivity. But for such a device, one of the key technical questions will be how to obtain virtual object with your captured images. This problem is very long, very old vision and computer graphics problem. But fortunately, recently, there's a very good solution called neural rendering or neural radiance field. It enables us to train a very small model with your captured images. And then you can render any image from any camera viewpoint. Briefly introduce this technology. So we train very small model like this one, simple multi-layer perceptron. That's it. As a result of training, you will obtain a trained multi-layer perceptron. And then you can render the image from any viewpoint. So let me briefly introduce how we can train this one. To do that, we need to know how to render the image. So as you know, in order to render an image, you have only to know the pixel colors. So you have only to know how to calculate one pixel color. That's enough, actually. So if you see on the left, we have an image. In order to obtain one pixel color, you will shoot a ray from camera center through the pixel in the image into the space. You can think about a ray. On the ray, we have sample points, as you can see here as dots. On each sample point, you have 5 data, 3 3D coordinates and 2 angles of the ray. And using them, actually you run the MLP to obtain RGB color and some output called density corresponding to the probability of having surface at that point. So on each sample point, you have RGB color and the surface probability. And then the remaining step is only one thing. You do weighted summation of them to obtain the color of the pixel. Very simple, as you can see in this equation. And after obtaining the color prediction, this is a training. In the case of training, you need to know the training loss, the error, right? You already have the pixel color because the pixel color can be found in your captured images. So you already know pixel color, you have color prediction, you know the training loss, and you do backpropagation to update parameters in the MLP. That's it. Very simple method, very powerful. That's why if you can train one model per object here, you can obtain quite good rendering results, as you can see here. Until now, the story is fantastic. But we cannot benefit from this technology in terms of real-time rendering on mobile devices because we have computation cost problem. So let me briefly explain what the problem is, assuming a real device, real VR device like this spatial resolution and frames per second. So as I mentioned, in order to render the image, we need to know the pixel color. So let's check the number of pixels we need to handle per second. So spatial resolution by 90 frames per second will give the number of pixels you need to render every second, right? And for each pixel color, you need to shoot a ray, and on the ray, you need to sample points. Usually, we have 256 sample points per ray. That's why we have 256. And then finally, on each sample point, we run small MLP. Even though the size of MLP is small, the number of executing that small MLP is huge. The frequency is huge. That's why the total computation cost is very large. Even in the case of H100, you cannot benefit real-time rendering with this technology. However, since the introduction of this technology in 2020, in only 3 years, we have significant improvement in compute efficiency. So now we talk about real-time rendering even on smartphone. So in the following slides, I will explain how can we obtain such a drastic improvement in compute efficiency in algorithm optimization. Let's see the first technique called the Voxel grid, which is based on the pre-computation, actually. So this is one of the first papers where the authors presented Voxel grid as a fast rendering solution. As you can see on the left, we first train typical neural rendering model. And then we assume 3D box, as you can see here, 3D box. And inside of that box, you have sample points, equally spaced sample points called voxels. And on each voxel, you have 3D coordinates. Using that information, you can run the pre-trained NeRF model. And then you obtain some results, like density and some intermediate result shown here as variable k. They are intermediate results because in order to obtain final RGB color, we need small amount of additional computation. So we first store intermediate results in the 3D box. We call that Voxel grid model. And then we fine-tune that model by rendering image using the information there and by training the model a little bit more to reduce the training loss. And finally, we can obtain the Voxel grid like that. So when we use Voxel grid, in order to obtain one pixel color, as usual, we shoot array and we take sample points. But on each sample point, you don't have to run MLP. You have only to look up 3D table. Voxel grid is a 3D table. And then you can use the information of voxels near the sample point. So that's how we can significantly reduce the computation cost during rendering time. And the authors of this paper found that we can go further. Before that, let's compare the frames per second. So as you can see in the table, at the top right corner, you see the frames per second of the original NeRF solution. Very small. However, bottom right, you can see real-time frames per second, real-time performance. So that's thanks to pre-computation. Inside of Voxel grid, we already prepare almost all the results, pre-computed results, and during rendering time, you do some additional computation. And the authors of this paper found that probably by exploiting the Voxel grid, we can have also faster training as well. Until now, I talked about fast rendering, right? But the original NeRF training takes days, tens of hours. But they found that probably we can train that model in 1 minute by exploiting Voxel grid as well. So they found that instead of doing initial NeRF training, probably we can start the training from Voxel grid. So the initial state will be randomly initialized values inside the Voxel grid. And then you handle them as model parameters, and then you do backpropagation. And they found that this approach gives very fast training, as you can see in this figure. So x-axis represents training time, y-axis image quality. As you can see there, even in the case of 1 minute training, we start to see quite reasonable image as the output of the model. So now we talk about 1 or 10 minute training as well. Let's see second approach based on mesh. So on your smartphone, we have very good graphics pipeline, mostly for games, right? On server GPUs, or you can also find similar efficient graphics pipeline. But this is about image generation, similar to gaming. So we should be able to exploit existing efficient graphics pipeline. So that's the second approach. So as you know, in the case of gaming, when we render some virtual object, we represent the virtual object with mesh, 3D shape consisting of many triangles and texture. And then, as you can see here, we go through some pipeline stages called graphics pipeline. And finally, you can render very realistic image. So we want to exploit that. There are two approaches. The first one is, with captured images, we can try to train that kind of mesh directly. That's one approach that I will explain in the following slides. And another approach is a little bit more conservative, but more efficient. We first train NeRF model, as in the previous approach, and then we convert it to mesh model. So I will explain this approach as well soon. Let's see the first one. In this case, if you have one image of your target scene, you run CNN, and the CNN gives mesh and texture as the output. So we train that kind of CNN model. So let's assume that we are doing training. So we generated the mesh and texture, and using the graphics pipeline, you can generate image, right? And then you can compare the generated image and training image, your captured image, and you can calculate the loss, and you can do backpropagation to update the parameters of CNN. That's how we train this kind of model. But when we train this kind of model, there is one key technical issue. So the question is how to run vertex coordinates of triangle by gradient descent. So as you know, mesh consists of many triangles, as you can see here. The triangles have vertices. So in order to improve the mesh, you need to be able to relocate vertex locations, right? But by gradient descent. That's the point. So this technique is called differentiable rasterization. So the basic idea to do this is to exploit the relationship between the vertex coordinate and pixel coordinate P. We have two relationships, actually. The second relationship is capital I represent pixel color. That will be kind of weighted summation of vertex colors, right? So we have two relationships between pixel color and vertex color, and in between we have barycentric coordinates, the pixel coordinate, and then we also have another relationship between barycentric coordinate and vertex coordinates. So using them, finally, you can calculate partial derivative like this one. So when we ask whether we can train something via gradient descent or not, the question is very simple. Can we obtain partial derivative? So as you can see here, we can have partial derivative of loss with respect to vertex coordinate, as you can see here. So we can train this model by gradient descent. But in this method is a little bit indirect solution because given an input image, as you can see on top right figure, given an input image, by running the trained model, you can obtain the mesh. However, we can directly train the mesh with captured images. That's the approach of mobile NeRF from Google. So in this case, let's assume that we already trained the mesh and texture. Using graphics pipeline, you can render the image, right? So I will briefly explain how we can obtain these two. So they start with initial grid mesh, like this one. This is a kind of combination of voxel grid and mesh, actually, grid mesh. And then, as usual, we should lay to obtain pixel color. And as you can see in this cross section, we will have the intersection points represented by the dots. They are now sample points. On those points, we run 2 MLPs in their solution to obtain the probability of surface and some feature vector. And then we do alpha composition or weighted summation, as I mentioned earlier. And then finally, we obtain the pixel color for the lay. That's their approach. So during the process, they train actually these MLPs, and they also change the form, the shape of initial grid, as you can see here. They are not regular, right? And then after the training, they exploit pre-computation technique that I mentioned before, which means at each intersection point here, they run these 2 MLPs and they obtain pre-computed result there. And then during rendering time, as in the case of voxel grid, they exploit the pre-computed results for very fast rendering. It's really fast, so you can even run this model on typical smartphone in real time, as this demonstration shows. Let's see the final technique. So here we first train very good NeRF model. And then using that model, you convert that model to mesh and texture. So let's assume that we already obtained the mesh. In order to render the image, what you need is shooting a ray per pixel. So here you see the intersection point, lay and mesh intersection point. If you obtain that 3D coordinates, you can look up the texture to obtain 3 vectors. And you can also look up another texture using the angle. So now I have 4 vectors. The remaining step is very simple. You have 3 vector dot operations. As a result, you can obtain RGB color. So if you check the computation cost per pixel, you need only 3 dot product operation. The computation cost is really small. That's why they report 1,000 frames per second performance in their experiments. Because for each pixel, we need only 3 dot product operation after looking up the texture data. So that's the current status. So in the beginning, I mentioned that we have computation cost problem, and the paper was introduced 3 years ago. And in the past 3 years, we experienced drastic improvement in computational efficiency. But that's not the end of the road, because in order to enjoy real-time immersive photorealism, we have still very long way to go. Let me show you one example we need to address. So in these cases, you see different rendering depending on different writing condition, right? Simply speaking, in the original NeRF solution, we cannot support different writing. But in order to support different writing, we need to model surface material, and we need to be able to consider different writing condition and shadow and indirect illumination as well. But everything requires additional computation. So we have many orders of magnitude higher computation cost in this case. The second direction will be video. So here they may look like typical video, but we call them free viewpoint video. So which means you can see the video from different viewpoints, different from the viewpoint we had when we captured the video. So in order to do that, we need to be able to handle the movement information as well as static scene information. So we need additional computation as well. And sometimes the model size is very large in this case. And if you go outside, we need to be able to model very large space as well. So in this example, they try to model very large space, 1 kilometer by 1 kilometer space. by training many local models and by using them efficiently. And finally, they can obtain very large scale rendering like this. So the technology is available, but the efficiency is still a problem. That's my message. And finally, multimodality. In this example, in addition to the typical 3D modeling that I explained, they also injected textual information to the 3D scene. Thanks to that, you can do new functionalities like text input-based object localization. So in this case, if you give a name of some object you want to localize in that scene, and when we render the image, the target object will be highlighted, as you can see in these examples. But to do that, we need additional computation to run probably language model together with neural rendering model. So that's why I mentioned that we still have a very long way to go to enjoy real-time immersive photorealism. However, when looking back the past 3 years, we already had very drastic improvement in computational efficiency. So I expect probably in 3 or 5 years, we may have similar improvement in computational efficiency to enjoy this kind of nice functionalities. Okay? So thank you for your attention.